Okay, short version. Christopher Bishop here to give a talk from Stony Brook.
Thank
Go
you.
ahead, please.
So the title says optimal triangulations of polygons, but optimal just means that we're optimizing something. I have to tell you what that is. So the plan is to just talk a little bit about the history of the problem. And I want to write down a theorem which gives some necessary and sufficient conditions. And the necessary conditions are pretty elementary and they were previously known. And that's what I'm mostly going to talk about. And my contribution is to show that these are also sufficient conditions for something to happen. And that's kind of messy to write down the proof of. And I'll talk about some of the problems we encounter, some ideas for getting around them, but I won't say very much about those details. But there are a lot of open problems and results, and I'll mention some as we go along and mention more at the end. So I have a lot of things to say there. So there's different kinds of triangulations. You can triangulate by only connecting diagonals of the triangle. So that's not what I'm interested in so much. I'm interested in the center picture where you're allowed to add extra points called Steiner points. And if you're thinking of maybe taking a region and meshing it for like a finite element method, this is something that you might want to do. I don't know how to turn that off. Yeah. The third kind of, it's a crank call. The third kind of thing is called dissection, where you're breaking the domain into triangles, but the edges don't have to match up exactly. They can overlap. So a triangulation to me means a simplex mix. We have that. Okay. Now, I want the triangles to all be kind of roundish. I don't want long, narrow triangles that have very small angles and very big angles. And so to make them all as round as possible, what I'm trying to do is try to minimize the maximum angle that's used. So when I say optimal, I'm trying to minimize the maximum angle used anywhere in the triangulation. And so the best I could hope for is that they're all equilateral triangles, because the angles of a triangle add up to 180. So one of them has to be at least 60 degrees. So that's the best I could hope for. In general, the more round those triangles are, the better you would hope that certain numerical methods work. Particularly small angles tend to be bad for certain. Okay. Just a couple of definitions. Acute means all the angles are less than 90. Not obtuse means they're less than or equal to 90. Phi triangulation means all the angles are less than phi. So an acute triangulation, or sorry, a non-obtrusive triangulation is another word for a 90-degree triangulation. And phi of p is the best angle you can get for a particular polygon. So we're going to try to, the whole talk is about how to compute that number. You hand me a polygon, and then you start a stopwatch, and I have to compute what that optimal angle is as fast as I possibly can. So back in 1960, Braga and Zalgar proved that every polygon has an acute triangulation. They published this in a Russian journal. It was part of a topology paper about a combinatorial version of the Nash embedding theorem. And so it wasn't really known to the computer science or computational geometry in the West. As far as I know, the first reference to it is like around 2004. Now, you can't do any better than 90 because of the fact I just said the angles have to add up to 90. So if I have a triangle that has a 1 degree angle in it, very small, the other two have to add up to 179. And so one of them is at least 89.5. And so as the angles get small, there has to be a big angle somewhere else in that triangle to make up for that. So if you are going to do all polygons, including those that have tiny angles, you can't expect 90 degrees to be better, to be improved. But for a given polygon, where maybe the minimal degree is 10 degrees, maybe you could get down to 85. That would be the best you could hope for. 90 minus theta over the minute divided by 2, that's the best you could hope for. And we'll see you can actually do that well, much of the time. Now, there's a big literature on triangulating with good shapes and doing it as fast as possible. And I just tried to write down every computational geometer who might ever listen to this talk and who had some paper. If I've left you out and you contributed to this, I apologize. Okay. The basic end of the story, as far as I'm concerned, is that not only does every polygon have an acute triangulation, but there's one of linear size that you can compute it. Okay. But as I said, there was this big literature starting in 1988, but as far as I know, at least according to math reviews, I was looking through it, I couldn't find any citations to the Braga-Zalgar paper until around 2004. Then people realized the basic fact was already known long before. Now, I want to mention Steiner versus no Steiner points. So if there's no Steiner point, you can only use diagonals. When you want to cut a square, for example, there's only one choice. And you can't get anything better than 90 degrees. I mean, there's only two diagonals. Whereas if you allow extra points, the Steiner points, you can definitely do better. In fact, here's a triangulation that uses 72. I'll leave you to verify that, but I checked it many times. In fact, it does give you maximum angle of 72. That's the best possible. And this, we won't have any proofs in this, but one thing I will prove for you is that for the square, 72 is the best you can do. So this is an optimal triangulation. I stole that from, that's in David Epstein's Geometry Junkyard, but it's also in a paper of Gerber from 1984, which I think is even earlier. So it may go back later on. This is just a historical slide to remind you that if you're not allowing Steiner points, if you're just using diagonals, then for point sets, the minimal angle can be maximized by the Delaunay triangulation. And for polygons, it can be, the minimal angle can be maximized by something called the constrained Delaunay triangulation. I won't get into that because it's a little digression for what I want to say. But I just want to say that when you don't have these extra Steiner points, you only have a finite number of triangulations to consider. Of course, it might be, and a lot of them to check. But there is a optimal one because there's only a finite to choose from. And the optimal one turns out to be a famous one, at least for one version for minimizing the maximum, for maximizing minimum angles, the Delaunay triangulation. And if you flip it and you want to minimize the maximum angle as we want to do, then there's a n squared log n dynamic programming algorithm for this due to Ellsworth. I checked with him a few months ago, and he said he was not aware of any improvement to this since this was published in 92, I think. But what we're interested in is allowing as many extra Steiner points as you want. So you could take a polygon and you can keep throwing in more and more points, more and more triangles if you want to. And it seems very conceivable that you could just approach an optimal angle, but never actually attain it. That you have to go to the limit to get it. So here we're going downwards, but I'll just tell you, I don't like to keep secrets too much. I would just tell you that these numbers do limit on 67.5 in this, for this particular case, and that this will actually be attained for some finite triangulation. Well, you see some of the issues that are involved is that when we have an infinite number of parameters we could play with, it's not clear that there is a optimum. We could just maybe only attain it in the limit. Okay. So one of the main things that comes out of today's talk is that the optimum actually is attained, except in a couple of cases, and I'll explain what that is. The other thing is dissections versus triangulations. Remember, a dissection is like a triangulation, but the triangles don't have to meet edge to edge. So it's a more general concept. So if I ask you, how can I dissect a polygon? What's the best angle bounds I can get? Maybe I could do better because I have more flexibility. Triangulations are a proper subset of dissections. And so one of the questions is, could I do strictly better with this extra freedom? Okay. We'll come back to this a little bit later on. One case I want to point out to you is just when we have two equilateral triangles put together. This can be dissected into two equilateral triangles. The dotted line does it, okay? And each of them has maximum angle 60. So this can be dissected with angle bound 60. It cannot, there's no triangulation that attains that. And I'll show you. The reason is because if there was a triangulation of a polygon by equilateral triangles, 60 degrees, they all have to be the same size. Okay, if you have equilateral triangles that meet edge to edge, they're the same size. That means every edge of your polygon is an integral multiple of that fundamental unit, which means that if this had an equilateral triangulation, all the edge lengths are rational multiples of each other. And so if I just slide little triangles, so it's an irrational, so this is an irrational thing, there's no triangulation that can attain 60 degrees. Okay. But it's a lemma that you can get with an epsilon of it if you want. I won't say too much about this. It's a little bit messy, but the main idea is that if you have a polygon where all the angles are multiples of 60, the edges are aligned with the edges of an equilateral grid. They may not line right up on it. Maybe the edge lengths are irrational and you can't fit it. But what you can do is snap those points to a very similar looking polygon that is on the grid. And then you can define a mapping of this thing to this thing on the interior, which alters angles only by a little bit. And so these equilateral triangles become things which are almost equilateral. And in the paper, this takes like 2-3 pages to actually write it out all carefully, but this can be done. And this is the idea for the general approach to finding nice triangulations.
May I ask a question?
Of course.
Before I go on to,
Absolutely.
how does this somehow compare with the general statement that you made? That somehow the answer depends on, can be determined from the shape of the original. So if you start with a shape which only has 60-degree angles.
Yes.
You're saying that this trick would get you at 60 plus epsilon.
If you take a fine enough, you might have to take the triangles very fine to get that epsilon.
Yes, but how does this compare with your claims that the thing is achieved, never achieved in the limits? There's always a
It's sometimes achieved and sometimes not.
Ah, I see.
So for a 60-degree polygon, it's achieved exactly if all the edge lengths have rational ratios.
Oh, I see. That's one of the exceptional cases.
That's the only exceptional case, it turns out. Every other polygon it's achieved, except for 60-degree polygons with irrational edge lengths. Those are the only non-examples. I was shocked. So most of what I'm telling you, I'd proven it, and then I came back the next day to check the proofs, and this went on for like a month because I couldn't believe the things that the proofs seemed to say. And I'm hoping to communicate some of my sense of wonder at this. The general idea for finding an optimal triangulation is to take any old polygon you have and draw a model which looks basically the same, but only has these multiples of 60. And it has either a real equilateral grade in it or something which is within epsilon of it. And then we're going to use a conformal mapping, a one-to-one holomorphic map by the Riemann mapping theorem to move this thing over to here. And if you've taken some complex analysis, a conformal mapping preserves angles infinitesimally. Now, when we move a triangle from here to here, the edges become curved. So we're going to take the two endpoints and snap a straight line between them. When we do that, two curves that meet at a certain angle, we replace them by straight lines, and the angles might change. We have to estimate how much they change. That's one of the epsilon delta proofy kinds of things, which I'm not going to be worried about too much. But that's the basic idea. And what I want to tell you is, assuming everything works out as nicely as possible, what is the answer you get? And then assure you that everything does work out as nicely. Okay. Among the problems, I mean, if you know about conformal mappings, if you're trained like a complex analyst like I am, one of the first things you learn about conformal mappings of one domain to another is you can always map 3 boundary points on one domain to 3 boundary points on the other one. You get to choose. But that's it. You don't get to say where a 4th goes, or a 5th, or a 6th. Only get to choose 3. And here I have n, and I'd like those n vertices to map to those n vertices. So if n is bigger than 3, that has to be addressed. Okay. There's some other things. Basically, in the middle of the polygon, the mapping is pretty close to being an isometry, pretty close to being a similarity. So in the middle, things are basically preserved. The images over here are close to equilateral. Near the vertices, though, if I take a 60-degree angle and I'm changing it to 45, that distorts the angles quite a bit. So the worst distortion is at the angles, and that's the secret. The reason why you can compute the optimal angle quickly is because you really only have to look at what happens at the end angles. What happens in the middle or between the vertices, we can prove that's not going to be a problem. It's only what happens at the vertices, and there's only n of them. So somehow that's why there's going to be a linear time calculation.
Why is that a 7?
Degrees 5 or 7. Well, the next half hour is devoted to talking about 5 and 7. Okay. So Euler's formula. For an audience like this, I probably don't have to dwell on this one a lot. Bases minus edges plus vertices equals 1. So I guess I'm not counting the unbounded bases. So we're okay with this one. I'd rather write it slightly differently. Maybe this is well known, I don't know. When I have a triangulation, I'm going to label the vertices with how many triangles meet at that vertex. And I'm always going to call this L. It's going to be the labeling of the vertex. And I want to think of these as kind of curvatures. And so what I'm going to do is actually on the boundary, it's going to be the 3 minus the number of triangles, and then the interior it's 6 minus. So where 6 triangles come together, that's a 0 curvature vertex. Where 7 come together, 6 minus, and that's a -1 curvature vertex. And now we take Euler's formula, and we use the fact that every face has 3 edges on it. We can simplify it. And by rewriting it, we can make Euler's formula look like this, that the sum of the interior curvatures looks like 6 minus the sum of the boundary curvatures. And so to someone from Stony Brook, where they like differential geometry, this looks like the Gauss-Bonnet theorem, that the integral of the interior curvatures is a topological constant minus the integral of the boundary curvatures. And so I think this is well known, but I don't really know a reference for it. But there's this paper of Thurston, which I was talking about earlier, which uses this. And one of my referees said I should have quoted it. So it was because I used this formula, which he says Thurston knew, so I should have quoted Thurston. But I claim many people before that must have known it as well. I mean, this is not that difficult. Now, if I tell you that I have an angle bound, like everything is an acute angle, or everything has maximum angle 72 or something like that, I get to say more stuff about these curvature formulas. Okay. For example, suppose all my triangulations are acute. All the angles are less than 90. That means at one of these Steiner points on the boundary, I can't have just two triangles. Because if I had two at that, one of them has an angle bigger than 90, bigger than or equal to. So there has to be at least three meeting at all these flat vertices. That means all of their curvatures are negative. Remember, curvature was the label 3 minus the label. So if I take all those and throw them away, I'm throwing away all negative terms. That means that if I just look at the labelings of the original polygon, it's less than the sum of the interior ones. So for acute triangulations, throwing away the flat Steiner vertices, I know it always works in one direction. I'm just throwing away negative terms. So if I have an acute triangulation, I must have a labeling so that the sum of the curvatures of the labeling is less than or equal to the sum of the curvatures of the interior. We okay with that? So everything I'm going to talk about today is sort of on this level of logic. I mean, we're not going to say what happens if the Riemann hypothesis, is true or not true, or make fancy arguments. Everything is sort of on this level. Back to the fact that the angles sum up to 180 again. If you have, let me use the chart. If you have a polygon and you have multiple triangles meeting at a vertex, this is angle theta here. And I know that the angles are bounded above by phi and below by 180 minus 2 phi, and there's 3 of them, then this angle can be at most 3 times phi, 3 times the upper bound, but it has to be at least 3 times the lower bound. So when I give you an upper bound for my triangle angles, I automatically get a lower bound that comes with it. And at each vertex, the angle of the actual vertex has to be the number of triangles times the upper bound, and underneath it has to be the number of triangles times the lower bound. And so this we call, if you give me a labeling, it's called the phi labeling if it satisfies these inequalities. So if the labeling comes from a triangulation, it has to satisfy this. Now, if you just give me a polygon and you put numbers on the vertices, you label them, then ask me, is there a triangulation that has that many triangles at those vertices? It better satisfy these inequalities. That's a necessary condition. It's not the only necessary condition. Suppose that instead of being less than 90, all the angles are less than 72. That means there can't be a degree 5 vertex in the interior. At a degree 5 vertex, there's at least one angle which is equal to 72 or bigger. So as soon as you tell me there's no degree, as soon as the angles are small, there's no degree 5 vertices, this sum of the interior curvatures, there's no positive terms anymore. They're all 0 or negative. And so the interior curvature has to be less or equal to 0. And because it's acute, 72 is less than 90, the labeling has to be less than 0. So not only does there have to be a labeling that meets these inequalities, but you have to have the curvature of that to be 0. And if you go a little bit, follow this logic further, you can prove that this is optimal for the square, okay? I showed you this 72-degree thing before, and I said we would prove it, that you can't do any better. Suppose we could do better. Suppose that there existed a triangulation with angles strictly less than 72. Then there are no interior vertices of degree 5. Once there are no interior vertices of degree 5, because this curvature is 0, and this curvature is the, sorry, I'm skipping ahead. If there's no angles, if all the angles are strictly less than 72, that means that there's a phi labeling where the curvature is negative. What that means is that there has to be one of the corners where the number of triangles is at least 2 at that corner. Otherwise, you have a negative number being a sum of positive or non-negative things, and that's impossible. But if you have two vertices, so if you have a vertex of curvature 2, I'm sorry, read what's on the slide. It's correct. What I'm saying may or may not be correct, but the slide I know is correct. If you have all the angles are less than 72, you end up deducing there's a corner, there's one of the vertices of curvature bigger than or equal to 2. That implies that there's a corner that only has one triangle meeting it. If there's one triangle in that corner, it has 90 degrees. That's a contradiction because 72. So it's written down correctly. I'm sorry, and say it didn't sound convincing the way I had meant it to sound when I said it. But this is a proof that you can't do better than 72 for the square. And the goal is just to recreate this argument for every polygon that exists. Define a triangulation that attains a certain angle bound and then prove by arguments like this you can't do any better. Now, once you drop below 72 and you get down to this, which is around 64, once the angles are that small, it shows there can be no vertices degree bigger than 7. If you have a degree 7 vertex, one of these angles here has to be bigger than 360, and that implies that one of the opposite angles has to be bigger than 450 over 7, and this leads to a contradiction that, leads to a contradiction. You can't have that. I'm being a little sloppy here, but hopefully you'll forgive me. The point is that when you have a polygon, if you have a phi triangulation, then if you take the labeling for that triangulation, well, it certainly exists. If the angles are less than 72, the curvature of that labeling has to be non-positive. And if the angles are smaller than 450 over 7, in fact, that labeling has to have curvature 0. And the question is, if there exists a labeling that satisfies that, is there a triangulation that goes with it? The answer is yes. That's the new thing. So the theorem says that for angles between 60 and 90, a polygon has a phi triangulation if and only if those conditions that came from Euler's formula hold. And so this was these, as I mentioned before, these were found by Joseph Gerver back in 1984. Be necessary. Oh, can't go backwards. I'll go back. Okay. So in 1984, and I guess proven to be sufficient by myself in 2020. So about 40 years later. So this theorem is kind of messy looking. What it basically tells you is a yes/no answer. If you give me a polygon, basically a list of angles, and say, here, what about phi equals 73? What I can go through is I can check and see if there's a labeling that meets these criteria. And if there is, then a 73-degree triangulation exists. If there's no such labeling, it doesn't exist. Well, how easy is that to check? Turns out it's very easy to check. So this, although it looks a little complicated, this theorem has many simple corollaries and consequences. I'm going to spend the next 10 slides just giving you easier theorems that follow from this one, which is admittedly not as pretty as it might be. The first thing is that in these conditions, there are less than or equal signs in front of the 72 and the 5/7 90. And what this means is that if you have a sequence of triangulations for phi 1, phi 2, phi 3 converging downwards to a limit, that limit is in the same line as the sequences. Okay. And so if the triangulations exist for phi plus epsilon for every epsilon, then there's a triangulation at the limit point. Doesn't work for 60 degrees because there's a strict inequality there. But we know that happens. We already saw an example with the two equilateral triangles where the triangulation did not exist. But if you have one angle, if you have an angle which is bigger than 60 or which is not a multiple of 60, somewhere in the polygon, then the optimal triangulation exists. It's only when they're all multiples of 60 there's some doubt. Okay, so that was surprising. I didn't expect that. So that caught me off guard. That was a kind of a slightly shocking thing to me. Another fun thing is that these conditions only depend on the list of angles in the polygon. Doesn't matter what order they occur in, or it doesn't matter how long the edges are. And here are two polygons that have exactly the same sets of angles. I colored them so they'd be same. Green angle is 135, and the white ones are all 90, and there's the same number of dots. So just looking at this picture, the theorem says the optimal angle, whatever it is, I don't know what it is, but it's the same for both of them. Okay. So that was that's something that falls out of this. Here's my favorite. I told you Gerver proved these conditions were necessary. He actually proved that they have to happen whenever you have a dissection, a phi dissection. And I proved they're sufficient to give you a phi triangulation. So the existence of a phi dissection implies there's a triangulation of the same angle bound. So for every bound bigger than 60, having a dissection doesn't give you any more freedom. You can't get a better angle with dissecting than you can with triangulating. So the simplex condition doesn't add it. So I'm very interested in collecting as many theorems about dissections as I can and seeing if they can be all improved to triangulations. So there's one case where I've done this already, but I don't know that many theorems about dissections. But now I'm thinking they just automatically always improve from dissections to triangulations, because that's what happens here. More stuff. So for a given polygon, phi of p, which was the best angle bound you could get for that polygon, it's the smallest phi that you can that satisfies these conditions. So it's the infimum of these. Now I have several slides about how to compute what this optimum is. I don't know if you're interested in hearing that kind of linear versus quadratic complexity kind of things. I can skip those slides, or I can go through them for a few minutes, or you could fall asleep.
At least one example.
I'll give you a few examples. Okay. The first calculation is, well, given a phi, like given 84, how fast can I check whether the answer is yes or no for that particular angle? Is there a triangulation or not? That turns out to be pretty easy to check. So the point is, I don't know if this diagram will make much sense, but remember that the angle theta of the polygon, if you label that vertex with an L, that means theta had to be between L times the maximum allowable angle and L times the minimum allowable angle. And so the horizontal axis here are the phis, and at 60 degrees, 180 minus 2 phi and phi, they come together. So for 60, those are the same. And as you move out over here, when phi is equal to 90, it becomes a triangle. So the larger phi becomes, the bigger the gap becomes here. And what we need are all the angles to be in one of these triangles. So being in the bottom triangle here says that this is hold with L equals 1. Being in the second triangle says these inequalities hold with L equals 2. The third triangle, L equals 3, and so forth. So we need all the angles to be in the shaded region, okay? So we get to deduce a bunch of stuff here. For example, this is the line 72, the dashed line. To the right, this is a connected set. If you take a line here, this is one interval, it's a ray. Once you move to the left of this, there are gaps. For example, here at 65, you can't have any angles in there, or any angles in there, or any angles in there. But to the left of 72, once you know what the minimum angle is and all the angles are above it, you're set. And above 72, the labeling doesn't have any curvature condition. They're just, is there a labeling, but no curvature? That means that whether you have a phi triangulation only depends on the minimum angle in the polygon. That's it. No other property of the triangle. And so that we get a corollary on the next thing, I'll point it out here, that for small angles, that once you know the minimal angle is okay, then the maximum angle is just 90 minus 1/2 the minimum. That was the optimal thing you could do. I explained before. To the left of 72, so when the minimum angle is bigger than this, then things get a little more complicated because of the shape of the region was a little more complicated. But what you know is, in that case, you're definitely to the left. You're underneath 72 degrees. Right. Now, the square is not particularly special. It turns out that for anything that has axis parallel sides, the answer is always 72. No matter how complicated it is, you always get 72 for that. If you have all the angles are bigger than 144, I think this is kind of interesting, because one application of polygons would be to take a smooth domain and approximate it by a polygonal thing and then do your thing on the polygon. But if you're inscribing a polygon into a smooth curve, the angles are all close to 180. They're in this case. So when you have a polygon inscribed in a smooth curve, 72 is the best you can do. Okay. And so the number 72 occurs quite a bit here, you've noticed. There's a reason for that. Everything in that has a reason, right? So You can think of this mapping that from a polygon, you compute this optimal angle bound. So it's a mapping of polygons to numbers. And we'll think of polygons as being a subset of R2n. So we have, for each vertex is 2 real coordinates, and there's n of them. This turns out to be a continuous mapping. So the inverse image, if you say, what's the set of polygons that have that bound, that's a closed set. There cannot be uncountably many of them that have interior. You can't have uncountably many disjoint open balls in Euclidean space. So mostly the set of polygons that have a certain angle bound is actually a codimension 1 subspace of Euclidean space. There's only 2 examples, 72 and this other one, the 2 points where we split in the curvature, where the curvature condition shows, those sets have interior. They represent open blobs in the space of polygons. So for example, if you take something where all the angles are bigger than 160 and you perturb it, the angles are now still bigger than 155. So the optimal angle bound is still 72, no matter how you wiggle it. That has interior in the space of polygons. But there's only two polygons that have that, only two bounds that have that particular thing. Just to test this, I created 1 billion random tengons, and I computed the optimal angle bound for each of them. And I plotted it in a histogram. So when I did my very sort of informal experiment of choosing random tengons, and the tengons were not really tengons, what they were 10 tuples, which added up to whatever a tengon angle has to. It's 180 times 8, 10 minus 2. And I computed the angle bounds for that. You do see this spike at 72, which is the open blob of polygons which have that optimal thing. Now around 64, there should be another spike for the other open set. It's not here. I'm not quite sure why it's here. The theorem says that there's an open blob if the number of vertices is large enough. And the example in my paper has like 30 or 40 vertices in it. So 10 may not be big enough.
What the heck?
The ghost in the machine.
Getting too close to the screen.
Yeah.
Chris, move away from the screen.
Is that the problem?
That's the illusion on my part.
Is my magnetic personality interfering with the Wi-Fi in some sense?
Yeah, probably.
All right. So a couple of problems here would be, I know that for large n, there is going to be a blob, a spike around 64.26. But maybe tengons were not big enough, but how big would n have to be? And the other thing is, well, what's a better model of a random polygon? That's something I would really like to know. So, all right. This is the one of the final things I'll say. And now, and after this, things are going to get a little blurry. We'll see. The optimal angle bound, it follows from this statement that you can compute what the optimal angle bound for an n-gon is in time order of n, linear time. And this isn't one of these algorithms like Chazelle's triangulation of a polygon that you can't actually code up. This you could actually write the code to do it this fast. And so I wrote some code which is not this fast, but which there's a very simple way of computing it to 20 decimal places very quickly, and that's all I did. But you can compute it exactly if you want. I do want to point out that if you have a rectangle with 4 vertices, if you're going to have one of these triangulations with very round triangles in it, then you're going to need a lot of them. You're going to need on the order of R triangles. So the number of triangles you need is not bounded by the number of vertices. It depends on the geometry. But there's no way around that. That just has to be the way it is. Now, there are some slides I could skip, but maybe I'll just throw them in. I'm always a little bit concerned about, I have 4 slides describing this linear time algorithm for computing the optimal angle. And maybe I'll just say what goes into it, but I feel a little queasy about it. Of course, it would help if I knew where to stand or what to do so that the slides work. The first thing you want to do is find the minimum angle of the polygon. You can clearly do that by going around the polygon in linear time and seeing what the minimum is. We know if the minimum is less than 36, what the maximum angle is. It's 90 minus, that's one of the corollaries, so we're done in that case. If the minimum angle is very big, bigger than 144, the answer is also 72. We're done in that case. So it's only when all the angles are not too big or not too small. So it's sort of like Goldilocks. When they're sort of in the middle, that's where the work is. That's where you have to work on it. I would just say that after about a page of calculations in the paper, it comes down to computing two things. The smallest phi for which there exists a phi labeling at all, and the smallest phi for which there's a labeling of curvature 0. And once you know those two numbers and all the angles, it's just a hand calculation to figure out what the optimal angle is from that. That I hope you'll just take my word from. Nobody move or breathe. Okay. Computing the phi infinity, that turns out to be really easy. You basically, for each angle, you just have to compute the minimum and maximum of something, which comes and goes. But that's very simple to do. It's no harder than computing the minimum angle. Computing the phi 0 is what takes the time. The picture is here. So for each, if you give me an angle, I can compute the largest possible curvature. At each vertex, I just take the biggest labeling that could possibly work. And at each vertex, I take the smallest angle labeling that could possibly work. And it's not hard to compute these two functions, which for every phi give you the largest possible curvature of a labeling and the smallest one. And what we're trying to find out is what is the smallest phi for which there's a 0, for which is 0 curvature. So we start with lots of possible curvatures, and then there's fewer and fewer. The smaller phi gets, the smaller the range of curvatures is. And when 0 leaves that range, that's what we want to compute. And the places where these jump are basically integral multiples of the angles of the polygon. So we know what they are. There's only an order n of them, but they're not sorted. If they were sorted, we could go faster. But we can't afford to sort them because sorting takes n log n, and we're only giving ourselves n. So we got to find this point, but given the vertices of the polygon, but the polygon vertices are not sorted for us. But what we can do in linear time is find a median. You can find the median of a list in linear time. And so what you do is you look at the possible places it could be and choose the one in the middle, like this one. And you compute the upper and lower bounds. And in this case, 0 is in that range. That means the ones to the right can't be the minimum angle. The minimum angle has to be to the left. So you throw away the ones to the right, half of them. Then you take the median of what's left and you look at it and you see, is it to the left, is the optimal thing to the left or right of that? You throw away half of those. And then you take the median of what's that. Each time you throw away half the data. And at the next step, the work you have to do is half as much work as you did the last time. And so it adds up to be linear. So by iterating the median instead of sorting, you can find that optimal thing when 0 leaves the range of possible curvatures. So the next slide says that, but since I just said it out loud, I won't make you read it. Now the proof, remember the proof said we were going to take an equilateral triangulation of a model polygon that sort of looked like our polygon and then move it over by conformal mapping. And that there were a bunch of technicalities to be dealt with. Okay. I want to mention 2 or 3 of those technicalities and wave my hands a little bit around how we deal with them. First, I can't get into the building for like a half hour because I don't have the right ID. And now I can't get the talk. Okay. So one of the difficulties is that when you have a closed polygon, the interior angles have to add up to a particular sum. It has to be n minus 2 times 180. Okay. If you take a polygon, you might think, let's just snap it to the nearest multiple of 60. So a 90-degree angle might go to 60 or 120. It's halfway in between. 80 should definitely go to 60. You know, that's sort of obvious. Turns out that doesn't always work because when you do the snapping to the nearest multiple of 60, it may not add up to the right sum. So you got to get around that. That's one difficulty. Here's some other difficulties. Remember the issue I said in a mapping, conformal mapping, you can only specify 3 boundary points. So for those of you who know low complex analysis, there's something called the Schwarz-Christoffel formula for the conformal mapping of the disk to a polygon, where the exponents, these things are the angles of the polygon. Those are things we know. And the zk's in the formula are the points on the unit circle that map to the vertices of the polygon. So the Schwarz-Christoffel formula says, if you know what the conformal mapping is, and you know what points map to the vertices, then you know what the conformal mapping is, because you can plug them into the formula. It's kind of circular. Okay. So what you have to do in practice is solve this nonlinear equation. But there are many papers on how to do this. And we'll just assume we know how to do this correctly. So the way that we deal with the finding conformal mapping is, for the target polygon we're dealing with, we find the Schwarz-Christoffel map that maps onto that polygon. We then keep exactly the same ZKs. These are the points on the circle that map to the vertices. And we just change the angles in the Schwarz-Christoffel formula to the angles we want to have, the multiples of 60. That defines an image polygon of the disk. And then the composition of these two Schwarz-Christoffel maps is the conformal mapping of one to the other that maps all the vertices to all the vertices, not just three of them. So that's the idea for getting around that. Again, if you're not a one variable complex analysis person, there's a lot to take in there, more than you could take it in 1 minute, I think. In general, though, we're going to map an equilateral grid over to a more general polygon. The trouble with this, let's just jump to the main point. In this equilateral grid, everything interior has degree 6. And we know that for some polygons, you have to have degree 5s and 7s. They can't possibly arise from this picture. So this can't work when Euler's formula says there must be interior vertices degree 5 or 7. How do we, for example, get a degree 5 vertex to be the image of a degree 6 vertex? We can't. But there's a trick. Of course, there's a trick. You can have degree 5 vertices in this picture. Okay? Let me show you where they come from. I can have a degree 5 vertex on the boundary. I can then map that to a picture like this, where these two sides of the slit get identified to that side. And so this picture is the one I drew on the blackboard. I wanted that vertex to become identified with that, and that to that, and that to that, and that to that. So for those of you online, I want to identify these slits, but to make it a triangulation, vertices on the top edge have to get mapped to the same places that vertices on the bottom edge do, so that the edges line up. Otherwise, I only have a dissection. I won't have a triangulation. And this is a cause for worry, because I only get to choose where 3 of them go at most in general. Okay, there's that problem again. And here I have 4 or 5. The way out of it is I have extra degrees of freedom by not making this a straight line, but by curving it. By making that curved, I can move where the points map to. And it turns out it's possible to choose a curve so that they match up exactly. So that an interval of length t here and t here, they both map to something of equal length over here. So things match up. This is what's known in the business as a conformal welding. We want to find a conformal mapping where the boundaries are identified according to a homeomorphism that we specify ahead of time. So there's a big literature on this. But in this case, it turns out you can do this with explicit formulas. We don't need to quote any fancy theorems. You can build these maps out of logarithms and exponentials and power maps. So you can make a conformal mapping of this polygon to this polygon so that 2 boundary edges get identified to a curve. This is actually curved. This is an actual mapping where I did it correctly. But the amount of curvature is only about 3 degrees between the 2 ends. So it looks straight to the naked eye. But if you were to blow this up, the tangent here is about 3 degrees different from the tangent there. Okay. So you can imagine that in a paper where this is all written out, this is starting to build up. What about degree 7? Sometimes we need degree 7, so we have to replicate this picture with a boundary vertex that has 7 equilateral triangles around it. How can you do that? I brought you an example. I cut it out of paper. Here's a polygon. This vertex has 7 equilateral triangles around it. 1, 2, 3, 4, 5, 6, 7. The only trouble is that this thing isn't a planar domain. It's a Riemann surface built out of equilateral triangles. But we don't let that stop us, because everything we've done so far doesn't depend on it being a planar domain. It works for Riemann surfaces. And so we have to introduce the notion of what we mean by a polygonal Riemann surface. It's basically something that lives over the plane and projects down into it. It might be 2 to 1 in some places. And when we take a Riemann surface like this, it's simply connected. There's no closed loops in it that aren't trivial. So this is conformally equivalent to any other simply connected domain by the Riemann mapping theorem. The version of the Riemann mapping theorem that works for Riemann surfaces, but there is such a thing. you can map a picture like this to a picture like this, so that this degree 7 vertex in the image becomes a degree 7 interior vertex. And again, the two red edges are identified, so all the vertices match up and become a triangulation. So we can insert degree 5s and degree 7s where we need them. And given all these tools and tricks, if you give me a labeling of the vertices that has the right curvature, I can build a triangulation which attains the optimal angle bound by basically doing all degree 6s, except for Euler's formula kicks me in the back and says you must have degree 5 or 7. I insert them by these slits. And it all works out. Now, the proof in the paper, I'm very sloppy about doing all this. And the triangulations I create have zillions and zillions of triangles, many more than you possibly need. So a follow-up project will be to try to do it reasonably efficiently. But for my concern was just to get the angle bound and show it was attained, not to show that I could get within like a bounded order of the right number of triangles. That remains to be done, but I think it's doable. Something I want to come back to. There's a question? Yep.
So I don't have a background in computer science, but so in this welding thing, you're still fixing, I guess, up to 3 points, right?
Right. Well, what happens is I'm taking a surface like this, and I want to map it to something like this. So I take these edges together so that the vertices match up correctly. Now, this doesn't look planar, but in fact, there is a theorem that says that this can be pushed into the plane by a conformal mapping, which distorts the angles, not very much. Okay. And so, yes. So one reason why this is kind of a long and technical paper is because it uses a lot of elementary things, but then it says, oh, but we also want to not just use the Riemann mapping theorem for polygons, we also want to use it for polygonal surface polygons. And so it takes a lot of writing to explain everything. But the basic ideas are, I hope, reasonable.
Sorry, I guess it's not actually about that surface. It applies to the last construction too.
Yes.
Are you fixing the vertices?
No. Okay. So what's happening in this map is I am able to do this mapping of a region like this, a region like this. So all the boundary vertices do go to boundary vertices over here. And these vertices do go over here. And the two slits get identified. And what happens is that if you take the vertex here and the corresponding vertex here will get identified in the image to this. In fact, what happens is that if you take 2 points of an edge, which are both distance t from this vertex, you go down t here and t the other way, those 2 points will get identified.
But sorry,
it's not obvious you can do that, but you can do it. I prove you can do it.
But the endpoints of the triangle, are those given to you by the theorem, or are you fixing those ahead of time?
I'm fixing those. So this picture here is a fixed picture.
Okay.
In a different sense than the obvious one.
But then doesn't that mean as you expand to potentially more of these things, you're doing more than one of these in the end, right?
Basically, there's one of these pictures per application of the theorem. So this is, so if I have to insert more than 1 degree 7 vertex, for example, this picture will be going on. I may have some big complicated polygon, and I may have to insert a slit here and a slit over here. What will happen is that I will use a picture like this in a neighborhood like this to construct the triangulations here. And then away from here, I will have another way of constructing a triangulation. But there will be an angular region. So this picture should be thought as being very tiny. And then there's a big, thick annulus around it in which I have 2 ways of defining a triangulation. But they're very close to each other. And I show that I can basically use a partition of unity to go from one to the other. And so part of the construction is to break the neighborhoods of the vertices and other points where you have to. There's slightly different conformal constructions in the different regions. And then in the boundary regions, there's what I call an interpolation between triangulations. But if you interpolate in these, the only big angles are near the vertices. So in these angular regions, all the angles are between 60 and 61. They're all very close to 60. If I take 2 things which are almost both equilateral grids of almost the same size, I can merge them and the new angles are at both 62. I just lose a little bit extra. but I'm working below whatever that maximum is. The maximum is not 60. There doesn't apply to 60, it applies to anything else. So if the angle is 60.01, I'm doing this in a region where I'm working at 60.0001. I'm working underneath the bound. That's one reason why the numbers blow up, is because of an issue like that. Okay. So I'm wondering if I should pause now or stop. What I have is about 5 minutes of open questions here. And then the PSLG questions, that's kind of like 10 more minutes. So that I was going to say for the really diehards after the questions and later on. If you like, I could spend a few more minutes talking about some open questions, or I could just thank you now for listening. It depends. You want me to go for another 5 or 10 minutes, or you want me to pause, stop now? We're at 6 o'clock or 7 o'clock, so.
I'm committed to hearing. Yes.
Let's
Go on a
try
little bit further.
Let's try the usual trick. Thank you, Chris.
Are there any questions that you have?
Could you please explain what you would have explained if you had?
I'll blame the technology a little bit. So one of the surprising things to me about this was that finite triangulations that attain the optimum usually occur, except in these 60-degree cases. Because I could have easily believed that there were situations where you can get closer and closer and closer to a optimum, but not actually get it. And a very analogous problem I thought about before is when you're triangulating a polygon and trying to minimize the total edge length, trying to find a minimal weight triangulation with Steiner points. This is a picture of one where if you take this X and move it down towards D, you go to a minimum, and given any triangulation, this will have shorter length if X is only close enough to D. But if you take X equals to D, these triangles collapse the segments. It's not a triangulation anymore. So this thing has no minimal weight triangulation. So Joe Mitchell asked me this question, whether you could do this. And after a couple of days, I came up with this example, and he says, it's no good because you have 3 collinear points on the boundary. You have one angle of 180 degrees. I meant, can this happen for a general position polygon? And that's still open as far as I know. Now, it's possible that minimal weight things always exist, except when you have this one special thing of collinear things made. That would be kind of like the optimal angle thing. They always exist, the optimal ones, except if you only have multiples of 60 degrees. And so I'm still very interested in this. I should point out, though, that I don't know if analogies mean much, but the analogy of my result for no Steiner points was basically the Delaunay triangulation, which is an old, well-known thing, and you can compute it in like n log n time. And then with Steiner points, I had to work harder to find the optimum. Now, if you ask this question with the Steiner points, what's the question without Steiner points? It's finding a minimal weight triangulation of a polygon, which is notoriously NP hard. So I don't know if that means anything, but the case I did was the Steiner version of something that was kind of well-known and in some sense easy. And the minimal weight question is the Steiner version of a problem which is notoriously hard. So maybe it's hard as well, or maybe that's an indication that the minimum doesn't always exist. I don't know. It's just random thoughts that occur to me. Another thing, I discussed this already. If I take my rectangle and I draw a model of it that only has 4 sides, I have to use an immense number of triangles if the eccentricity is big. That just works out that way. If I were to use more vertices, like remodel my 4-gon by a 10-gon, this thing does much better. So if I'm trying to get an optimal number of triangles, I have to be more careful about choosing the model polygon. My model polygons have the same number of vertices as the things I'm trying to triangulate. And that works for the proof, but it can be very inefficient. And by taking other models, we might do much better. For rectangles, we can do much better. And for rectangles, order of the eccentricity is the bound. That's the best you can do up to a constant. So can you make the analogous statement? Given a general polygon, can you find one of these 60-degree models so that when you use it to determine it, you're sort of within a factor of 10 or 100 or 1,000 of the optimal number of triangles? Can you compute the optimal number of triangles? Sounds like an NP hard problem, right? what's the absolute best number of triangles you can use? Probably it's not computable. And then everyone's favorite question is what happens in 3 dimensions? And again, I don't know. Everything is harder. You had Igor Pak here recently. He's one of the nice things he did was show that if you go to tetrahedra and you can see dihedral angles between the faces, you can ask whether a polyhedron can be tetrahedralized with acute tetrahedra. And the answer is we don't know. You might ask, can every polyhedron have an acute triangulation of polynomial size? And it's known that you can't even do it for the cube in R4. It doesn't exist. And in the cube in R3, these guys constructed an example with, I think the smallest known one has 1,300 tetrahedron in it. Obviously, computers might have been used in the finding of this object. But that already just shows you, like going from a square in the plane, we can use 14 triangles. And you go to 3 dimensions, you need thousands. So will a polynomial number do for any polyhedron? That's like the big question. And this is my official ending point. And then you can thank me again, and then the real diehards could ask me something else if they want. But, I'm sorry, you've been so patient, and I don't want to abuse your big picture.
Thank you again.